Hello everyone, welcome back. So now let's go through some group problem solving. So as always, grab a buddy to do this problem with you. Maybe if you don't have a buddy with you, grab a rubber duck or perhaps an ocelot. Yeah. Or, no, better than that, a platypus. They are amazing creatures. Okay, now that my silliness is ended, what are we given? Well, we're given a thin polymer plate, which is PQR. We're defining it by its endpoints. And it's formed such that the corner Q is displaced downward 1/16 of an inch to a new position Q prime. What do we want to find? We want to find the shear strain at Q prime associated with the two edges PQ and QR. Okay? The shear strain is associated with the edges PQ and QR. So let's figure this out. Actually, wait a second, what am I doing? Pause. Take a few minutes and see if you can do it on your own, and then come back and tell me how it goes. Now, you'll be talking to your computer, and it's a video, so I can't really understand you. But in spirit, I am hearing your answers right now. In the past. It's amazing. Okay, so pause, try it, then come back and see how you did. So, 3, 2, 1. You paused, you came back, and now you are ready to go. So let's listen to this and see how it goes. So, before deformation, the angle of the plate at Q was 90 degrees, or pi over 2 radians. Now we got to determine the plate angle at Q prime after deformation. Now, please remember that you always put your angles in radians. Radians. Any equation that needs an angle almost always needs in radians. It's not inside of tan, sine, or other trigonometric functions. Make sure it is radians. So, the difference between these angles is going to be the shear strain. So after point Q displaces down by a 16th inch, the angle alpha prime is going to be the following. Okay, so this is alpha prime. This will be beta prime. Okay? Alpha prime, beta prime. And it's always opposite over adjacent. Opposite over adjacent. So the 25 inches and the 4 inches, that doesn't change, but how far down they've gone does change. So what we get then is our angle right here is going to be 68 degrees, 0.075215, and this angle will be 21.6785. Lots of decimal places here. Keep them for now because in the end we're probably going to get rid of them. Now, our change in our angle is most definitely not 68 degrees or 21 degrees. That would be absolutely enormous. No, we're going to have to add those two together to figure out what the overall change is. And what we get is that, we had 89.753804, which is 1.566499 radians. This is not our change yet. This is just the angle in radians. So therefore, our shear strain is going to be pi over 2 minus that angle. And so it will be 0.004297 radians, or 4,300 microradians. Oop, a little bit too far there. So what did we do for this problem? Well, we figured out how far Q went down, so we know what its displaced position is. We then calculated the angles alpha prime and beta prime to see what that change in angle is afterwards. Now if you're wondering, I bet I could have done that with some vectors. You probably could have. You could have taken this point right here, made two vectors, and then maybe taken a dot product or something to figure out the angle between them. And if you wanted to do that, go ahead, more power to you. But this is another way to use just our basic trig functions and not have to bring any sort of calculus into it. Dot products are great, I love them, but avoid them if you want to. So, with that in mind, you did it. We solved it. 4,300 microradians. Well done. Okay, that ends this problem. I hope this video helps you. And next time, we'll go into one last group problem solving. So thanks for listening. Bye-bye.